So lean log model, what you should know actually here. So your independent variable is log form and your dependent variable is in linear form, means in original form. There is no log. Okay. So this beta 2, you have to know what is the interpretation of this slope coefficient. Okay. So it is clearly written over here. Right. Means if you will go to here, so directly it is saying how you will interpret actually beta 2. So you have to read at least this chapter, okay, to get not to complete chapter. I am just telling you to check the model specification. Means if you will go here, like at least log linear model, semi-log model, reciprocal model and logarithmic reciprocal model. At least you check the functional form, like suppose this one already I think you know. Okay, so this is a kind of exponential regression model, but we can convert into logarithmic by taking the log, okay, both the side. So quick revision you should do. Okay, and you can also see here in the note it is written how you are going to measure the different type of change. Okay, absolute change, relative change. In economics we calculate 3 different type of change when we say absolute change, relative or proportional change, then percentage change or percent growth. Okay, they are almost same, but how we can interpret in terms of regression. So first you read, I will take someday complete class on that. Suppose if you will go to this question is very interesting. The method used to estimate log linear model. Now you are sure what is a log linear model? How you will write? yi is equal to beta 1 plus beta 2. Is it a log linear model? ln x plus ui. Is it a log linear model? Just now I told you. Which type of model is this? Because there are actually like you have to know that this model, suppose for example log linear model and semi-log model. So sometimes we get confused by this, but what you have to see is the functional form. So semi-log model, it can be two type of semi-log model. You have to remember, one is log lean model and lean log model. Okay, and log lean model is basically used to measure the growth rate. Okay, like for example, you know this formula, right? Compound interest rate formula, isn't it? So which is basically where the dependent variable, please write it down somewhere, but it will be somewhere also in the document also. So if the dependent variable is expressed in the logarithmic form and the independent variable is in its original form, then we will call that model what kind of model? Log lean model. Are you getting? Log lean model, because here it is clearly given, if the regression is in logarithmic, it will be called log lean model. Later we will consider a model in which the regression is linear, but the regression means what? The dependent variable. Dependent variable means y is regression. Getting? So regressor is logarithmic, then it will be lean log model. So Madhusweta, what you told? Is it a lean log model? Can you see? It is a lean log model. But what was the question? Question was log lean model. Now what is the where we have committed the problem? We have to write like this: ln yi is equal to beta 1 plus beta 2 x plus ui. So this will be log lean model. Means x is linear over here and y is expressed in logarithmic form. Is it clear? And this will be called lean log model. So they are part of the family semi-log model. Is it clear, Sangeeta?
Yes, sir.
Okay, very good. Chinmay?
Sir, the lean log model means?
Lean log model means the dependent variable is in its original form and the independent variable is in logarithmic form. Okay?
Yes, sir.
And log lean, the dependent variable is in logarithmic form, natural logarithmic, but the independent variable is in linear form. Clear?
Yes, sir.
So, the method used to estimate log linear model is what? It is saying OLS after taking logarithmic, maximum likelihood estimation, instrumental variables, generalized least square. If you have remember, earlier also I told you where you are going to use, if there is instrumental variables, which method you are going to use. Which method?
Endogeneation.
Hmm?
OLS, sir.
OLS. You have forgotten. Okay.
Sir, endogeneity will do.
No, that is not a method to estimate. There is a note. I think you have not gone through the notes. Okay. Okay, I will come to that. Which method? So what is the answer? You are.
OLS after taking logarithm.
Can you check, Sangeeta? Is this the correct answer? OLS after taking logarithmic?
1 minute, sir.
Okay. So let us try to understand. So log linear model, already it is written over here clearly. Only the dependent variable is log. Lean log model, it is written clearly. Log model, the functional form is given clearly. So now step number 1, how you will do in this case? So you transform the variable for log linear model. You can create a new variable w called lny. Then linear log model, you can create a new variable for z which is equal to ln x. For log model, you can create both the variable in different. Means w is ln y and z is equal to ln x. So you can, after you transform, then you can use the standard OLS. As it is, you cannot use. So the model is linear in parameter after transformation. So OLS applies directly. So is the answer is correct, Sangeeta?
Sir, actually, which question number it is, sir?
I think it is 36 or I don't know. Question number 36, June 2016 question.
2016.
Now, after transformation, the model becomes transformed y plus beta 1 transformed x. Your x is also transformed. Means it is in the log model basically. So this is a standard linear regression model in the transformed variables. So all OLS properties will apply to the transformed model. And how you are going to interpret? We'll come to the other questions. Just quickly see, because this is very important. In log linear, what I was trying to tell, here it is written. In log linear model, so if you will interpret like if 1 unit increase in x will lead to 100 times beta 1 percentage change in y. Suppose you got, let's say that 0.5. So what you will do? You will multiply into 100. Okay? How much it will be? Madhusmita, 0.5 into 100?
Mhm.
It will take so much time?
50, sir.
50, na? So,
Yes.
so it means when x is increases by 1 unit, because here there is no change in, you have not transformed the x, you are using in original units. Okay, so you will interpret like this: if x increases by 1 unit, then y increases by 50 percentage. Okay, how much percentage change happens in y? 50%.
50%.
Okay, now you just see similarly lean log model. So our independent variable is transformed into logarithmic form. So if our x increases, means whenever, I told you earlier also, whenever there is a ln means elasticity or percentage, direct percentage. So we will interpret like this: 1% increase in x will lead to, simply how you will do, here you are multiplying, but here you have to divide. Okay, now we will say same question. Let's say that you got 10. Let's say that beta 1 you got 10. So you divide by 100. So how much it is? 10 by 100. How much?
0.1. Okay.
0.1.
0.1.
Okay. So it means uh, 1% increase in x leads to 0.1 unit change in y. Okay. So this is how you will be interpreting. And log model, it is the most useful model in econometrics also. So where we can directly interpret beta 1 as the elasticity of y with respect to x. It means how we will interpret 1% increase in x will lead to beta 1 times percentage change in y. Like if our beta 1 is 0.5, so simply you will directly write that, you don't have to multiply or do anything. You will write 0.5 percentage change in y. Clear, Madhusida?
Yes, sir.
So you have to remember some basic things, because we are talking about the transformation. Logarithmic requires positive values only. For negative number, you cannot transform into logarithmic. Yes or no?
Yes.
Sangeeta, you know this?
No, sir.
You have to read log and basic math concepts. And
Yes, sir.
Chinmay, do you know this?
No, sir.
That you cannot convert. You can check na, whether you can convert into log form. Have you ever checked? Like for example, if I will do simply, I will show you here. Just you take Excel, if you are having a laptop, and just you can transform it. Like for example, if I will go to Excel and I will show you, simply what I will do is, I will write ln of 100, let's say that. I got 4.60. Then if I will write log of 100, base is 10 over here. So I will get 2. Now if I will write what I told you, ln of minus
100.
100. Let us see. There is an error. Is it clear? Yes or no? So what we have learned? Logarithmic requires positive values only. It cannot take, you cannot transform the x value or independent variable if x is less than 0. You may need data transformation. And interpretation is coefficient have different meaning in log model versus label model. Label means what? Where you have not transformed the data into anything. You have kept the data as it is. Means if y is there, x is there, you have not changed anything. So this is called label model. Label means your data is at label. You have not transformed into anything. Then error term assumption, standard assumption error is additive in the log equation. This is not very important. So quick reference is here, the interpretation. So this table, please, already I have explained. Please. So normal regression which we used to write. So that is called level model. Okay. Log level log or log. Or if you are using linear, then it is a linear regression model. Then it is a log linear. You can use either this or that, lean log model, and this is log model. So level and linear we use synonymously. Okay, is it clear?
Yes, sir.
Any question, Sangeeta?
No, sir, but
Yes.
I can't find this question in the booklet, sir.
Let's see if it is not there. But let's say that this question is found, then you can use. Okay.
Yes, sir.
It must be there. It might be not there, but in the PDF I have closed the PDF, but I will cross check. Must be somewhere. It cannot randomly come. So log transformation is you have to transform first and then use OLS. Models become linear in parameter after transformation. You don't need special estimation method. Just you can use standard OLS on the transform data. So that is fine. This question is not there. Bruce-Pagan test, June 2016.
No, sir. June 2016 question is only not there, sir.
Where it is not there? Means the file you had sent me earlier is not there. Then
Sir, it is July 2016.
okay,
And in
then.
July 2016, we only 2 questions were there, sir.
Okay, no problem. Okay, let's see. Even if whatever the year, that we can cross check later on when I will send you this PDF. Okay, and you let me know if there is any discrepancy in the question. But we
This
can.
question is also not there, sir. Anywhere I have
Okay.
searched every question, but
Okay, we will see that. So Bruce-Pagan test is used to detect which? Autocorrelation, multicollinearity, normality or heteroscedasticity. Who will tell me? Bruce-Pagan test. Sangeeta?
autocorrelation.
Autocorrelation. 1. Your answer is 1. Sangeeta, your answer? Yesterday only I told you. I means last 2 class, if you will remember.
Autocorrelation, sir.
Okay,
But I'm
very
not
good.
very sure actually.
Okay. This is for heteroscedasticity.
Yes, I was confused only.
Because I told you many times that you keep a note in quick reference, only it is written also. Just you open the quick reference, you will find also that.
Yes, sir.
So, okay. First of all, you remember Bruce-Pagan test we do for heteroscedasticity. Okay, Chinmay?
Yes, sir.
So, Bruce-Pagan test detects heteroscedasticity. So, what we basically do in Bruce-Pagan test is we test whether error variance depends on explanatory variables. So, our null hypothesis in Bruce-Pagan test is H0 is variance of ui given x is equal to sigma square, that is homoscedasticity, means that is null hypothesis. So, if we will reject the null hypothesis, means alternate hypothesis is true, then there is a problem of heteroscedasticity in the data. But if we fail to reject the null hypothesis, then there is a homoscedasticity in the data. Clear? And this is how we do basically the procedure. First you will estimate the regression, then you will compute the standardized squared residuals, then you will regress the standardized residuals on the explanatory variables. Then you will compute the test statistics. One more thing which is very important, LM test. We do LM test. Okay. So that is basically we which is into n into r square, which follows chi-square distribution. So if the LM means the LM test statistics basically is greater than the chi-square critical value, whatever the critical value will is based on the question, then if it is greater than, then we will reject H naught. Then heteroscedasticity is present in the regression. So now what is the intuition over here? If squared residuals are systematically related to x variable, then variance changes with x. It means there is a heteroscedasticity. And if there is no relationship, then the variance is constant. There is a homoscedasticity. Like one example is given over here. For example, you have run the regression between consumption and income. So consumption is equal to beta naught plus beta 1 income plus u. And the auxiliary regression is how you will run the auxiliary regression. Auxiliary regression means the transformed regression is called auxiliary regression. So you have converted by following the previous method, and you have your dependent variable changed into the transformed variables. This is how you will get this UI. Means first you will check the original, estimate the original regression, and then you will compute the standardized square residuals, UI square upon sigma hat square. So now what are the other tests, which is how you will test? You will test is alpha 1 significantly different from 0. If yes, then the variance of consumption error increases with income. Then we usually have heteroscedasticity in the data. Then what are the other tests of heteroscedasticity? Please remember white test. Then another test is Goldfeld quant test. So at least this thing you have to remember. And what you will do, what is the solution if there is a heteroscedasticity? Sangeeta, you will use robust standard error. What you will use? Robust standard error. Is it clear?
Yes, sir.
Then what will happen to OLS coefficient if there is an heteroscedasticity in the regression? Means there is a unequal variance in the data. What will happen to the OLS estimator? I have already told you many times.
Inefficient, sir.
Beta 2 or beta 1, they are basically inefficient, means they are unbiased but they are inefficient. Clear?
Yes, sir.
So another method you can use, that is weighted least square method, when there is a heteroscedasticity is present. Okay, so these are the, but sometimes this kind of question also it comes. So please, even if like sometimes if it is difficult also right now, because I have not this thing, I have to take the data and I will show you, then you can easily remember that how we will do Bruce-Wagon test, how we will do White test or Goldfeld quant test. But at least you know, in Bruce-Wagon test we regress square of residual on x. In White test we regress square of residual on x square and cross product. And in Goldfeld quant test you split the sample, compare variance. But at least all these tests under heteroscedasticity, the null hypothesis is homoscedasticity. And if you will reject the null hypothesis, then only you are having heteroscedasticity in the data or in the regression model. So now, first of all, you don't have to, what you don't do, that Bruce-Wagon test is not for the auxiliary regression approach. Durbin-Watson test autocorrelation, not heteroscedasticity. Jarkwa-Bera test, it tests normality. Do you know Jarkwa-Bera test earlier?
No, sir.
Chinmay?
Yes, sir, I listen, but
Okay. So basically after I'll just show you. Suppose this is the regression model which we had estimated yesterday, isn't it?
Yes, sir.
So what you will do is simply you will check. Can you see? In
Yes, sir.
heteroscedasticity, these are the tests are there. White test, Brish-Wagon, and another test is here, Konker product. So that, but now we will test whether our residuals. Suppose you want to see the residual, I'll show you. Fitted versus. Uh, can you see? This is our predicted Y, and this is our regression line. Okay. So now, if I want to test, then what I'll do is I'll test this test, normality test. So in normality test, it is giving me actually idea that whether my error terms in the regression model is normally distributed or not. Fine. So sometimes we get actually Zarkov error test, sometimes it is reported, but you can see this is also close. Suppose here we did this test, okay, normality test, but I have to see whether Zarkov error test is directly given or not. I think here it is not given directly. So Ramsey test, then it is giving, but it will be easily done in other software. I have to check here. But what is important over here, that you can see that if I are doing normality of residual test, so you can say that is it coming, is there any heteroscedasticity? Let us do like that. So what is your conclusion, Madhusita? Is there any heteroscedasticity?
Yes, sir.
How you know?
No, sir. No, sir. Heteroscedasticity is not there because the null hypothesis error is normally distributed.
Very good. Chinmay, is there any heteroscedasticity problem in this regression model?
I don't know, sir.
You don't know? Okay. Sangeeta?
Sir, it is not evident, sir, anywhere to check heteroscedasticity, sir.
But here, once,
From which value we can check heteroscedasticity, sir? I'm not able to figure out.
okay, very good. Madhusita, we have not done heteroscedasticity.
But
We
sir,
have done
through the null hypothesis.
where null hypothesis is, what is the null hypothesis? Null hypothesis is normality of the residual. Are you getting my point?
Yes, sir.
So whether our error terms are normally distributed or not, I'll come to that. Let us do a heteroscedasticity test. White test we will do. Okay. So can you see over here? So just now what we had learned, that all the tests use that null hypothesis is homoscedasticity, isn't it?
Yes.
White and Bruce-Pagan also. So test statistics, how much we got? 2.254759. And the p-value, how much we got? 0.323881. Now Sangeeta, you will tell.
From
Means what is our null hypothesis? Our null hypothesis is that there is a homoscedasticity in the regression model.
yes, sir.
Clear? Now the result is in front of you. Now you should tell me whether there is a heteroscedasticity is present in this regression model or not. So simply, without wasting time, let me clarify it. So you have to
P-value is less than.
P1 is less than 0.05. Okay.
Yes, sir.
Then what will
So
be the conclusion?
null hypothesis.
What will be the conclusion if the p-value is less than 0. Means it is greater than 0.05, right? Then what is the conclusion you told, Sangeeta? Yes, can you tell me once again?
But if it is greater, then we do not reject the null hypothesis. If it is less, then we reject the null hypothesis.
Yes. You will say like we fail to reject the null hypothesis assumption of homoscedasticity.
Yes, sir.
Okay. We
Yes,
fail
sir.
to reject the
The null
null
hypothesis.
hypothesis. It means what? What was our null hypothesis?
That the homoscedasticity is there.
It means there is no problem of heteroscedasticity in our regression model. Is
Yes,
it
sir.
clear, Chinmay? I think Chinmay is not there. So, Madhusita, is it clear?
Yes, sir.
So, earlier what we did, you can see over here. So, here it is clearly written over here. I think null hypothesis is heteroscedasticity is not present. Test statistics, can you see over here? LM, which we have just now cross checked, right? So test statistics is LM test basically. We use or we do for LM test statistics. So how much p-value we got? 0.323881, which is much higher than 0.10 also. Hence, our null hypothesis, we failed to reject our null hypothesis which says heteroscedasticity not present. It means there is no heteroscedasticity in our regression model. Similarly, when Madhusudha got confused, when we tested, because this is a very important assumption, isn't it? Normality of residual. So, what will be your conclusion? Whether our error terms are normally distributed, Chinmay?
Yes, sir.
Whether our error terms are normally distributed? Here is given, na? Test for normality of residual. So, what is the null hypothesis? Error is normally distributed. And the chi-square test you did, you got 1.04. And the p-value you got 0.59. Simple logic is you have to look at the p-value and the null hypothesis. And if the p-value is greater than 0.05 or 0.10, so 0.59 is much bigger than 0.10. So what should be our conclusion? Because we failed to reject the null hypothesis which says error is normally distributed. It means our regression model is means the error in our regression model is normally distributed. Is it clear, Chinmay?
Yes, sir.
Okay. So now we'll go to the next question. This question is also not there. June 2016. So variance inflation factor is used for what? Let us see.
What the correlation of?
Okay. This is Madhusudha. Sangeeta?
Heteroscedasticity, sir.
So guess. You all are guessing. So Chinmay, what is?
Sir, heteroscedasticity, sir.
Because Sangeeta is saying, you are saying.
No, sir.
Okay, very good. So all of you have actually guessed the heteroscedasticity. I think this will be multicollinearity. First of all, you should know VIF is used, or it basically used to measure the variance of an estimated regression coefficient which increases due to collinearity. Because yesterday I think we have discussed that if there is a multicollinearity problem, do you remember question number 35 we are discussing, Sangeeta?
Yes, sir.
In case of multicollinearity, what will be the problem? If the OLS is unbiased,
Yes, sir. OLS is not unbiased, sir. It is only inefficient. OLS is unbiased and it is inefficient, sir.
it is inefficient, right?
Yes.
So now why it is become? Because the variance will increase, okay, due to collinearity or the linear relationship, okay. So VIF we calculate, VIF formula is 1 upon 1 minus R square, okay. So now what is the interpretation? So at least you can say, just to remember that if the VIF value is 1, then there is no multicollinearity problem. And if the VIF is 5, then you can say, but in this case there is a moderate multicollinearity. So if the VIF is 10, we will say there is a serious multicollinearity, okay. So now you can say if VIF is not calculated, suppose for example, let me check in this regression model. So how we will check the multicollinearity? Is there any problem if there is a test which is directly given over here? There is no test. Multicollinearity test is not present. Why it is not there, Sangeeta?
Sir, we have to put the multicollinearity test here. This is
Where?
only for heteroscedasticity, sir.
No,
Like the
no,
formula we have put only for heteroscedasticity.
no. The option is not showing over here. Why? Madhusida, why? Or whether we can check, first let me ask my question, whether we can check multicollinearity problem in this regression model?
Sir, no,
No,
because
sir, no. କାହିଁକିନା OLS is only able to find out the relationship between two variables.
You should have told that, sir, this is a single, first of all, this is a single variable.
yes,
If
sir.
let's say that
Yes, sir. Yes.
there are two variables and they are highly correlated. Okay, Chinmay, hello,
Yes, sir.
what is multicollinearity? If the two independent variables are there, yesterday also I had shown you,
Yes,
means
sir. But more than one
uh,
independent variable is linearly related.
means basically let's say that x1 and x2, there are two variables. If let's say that x1 is 5 and x2 is 10, if x1 is 10, it is 20. So what is happening? Linearly related, they are perfectly collinear, means we know x2 is 2x1. So what will happen? If there is a multicollinearity problem, the subpair will automatically delete x2. Okay? The subpair will only take one variable only. So that is why we will not go for multicollinearity test in the test section. Is it clear?
Yes,
Yes.
sir.
Chinmay, is it clear?
Sorry, sir, I don't relate.
No. First of all, let's say that you are running a regression. Y is a function of x1 and x2. These are two independent variables. Means it is your y is your consumption and x1 is your income and x2 is your wealth. Okay? Wealth is related to income or not? Sometimes
Yes,
yes.
yes,
Right? So it
yes,
means
sir.
there is a
Relation.
linear relationship. Means basically when you will find the correlation between x1 and x2, then you got 0.8. Okay? So obviously when there is a perfect linear relationship, of course there is a multicollinearity problem in the data. It means the correlation is very high. And when we had written this example, means if your x you are writing 1, 2, 3, 4 like this, and x2 is 2 times. Basically 2, this is 4, this is 6, this is 8. x1 is your, just to imagine, this is your income and this is your wealth.
Well,
So there is a linear relationship, no? Perfect linear relationship. Why? Because I am saying my wealth is 2 times my x1. 2 into 1, this is 2 into 2, so 2x2. So your x2 is equal to 2x1, right? 2 times. So this is we call linear relationship, perfectly correlated. There is a perfect correlation between this, you can say, two independent variables. So in this case, what will happen? This problem is basically known as multicollinearity. Okay, and by default, one variable will be dropped in the regression. That is what it is saying. Second, is it clear somehow, Chinmay? Later on,
yes,
I will
yes,
discuss
sir.
in detail. At least you should know the basic. Later on, we can discuss. So, VIF, first of all, you should know we use VIF, variance inflation factor, to detect multicollinearity. Is it clear? This test we do means we can find the VIF, variance inflation factor. But in your regression model, so we have only two variables over here. So VIF is we cannot calculate over here. Can you see over here? Is there any place where we can calculate the VIF? Is not given over here. But the moment you will run the multiple linear regression, suppose for example if I will change the data and I will do a multiple linear regression, you will see that VIF is directly given over there. Okay. Madhusita, is there any question on this?
Sir, actually, can you again repeat the VI?
First of all, why we calculate VIF, is it clear?
Yes, sir, to detect the multicollinearity.
To detect the multicollinearity problem in the data, right?
Yes, sir. Yes, sir.
So there are two things. First, definition is clear. So whenever there is a problem, what you should know? First, problem definition already you know, right?
Yes, sir.
Next thing, what you will do? Because when we are discussing a problem, we should discuss in detail so that you can remember. Suppose a problem is there. Suppose you are having fever. Now what you will do?
I take medicine.
You will take directly medicine, or you will
No,
check
sir.
which kind of fever you are having.
Yes, fast check.
Yeah, you can check it. Means you have to
Yes.
detect it. Detection of the problem is very important. right?
Yes, sir.
So now how I will find detection of multicollinearity, how I will do? First is, I think it is not written in this PDF, that is why I am writing. First is, if your regression model is high R square, okay,
Yes, sir.
but few significant T ratio, significant T ratio. Let us see if we can run a regression. I will show you the data. 1.5. Let me show you, because if I will show you it will be more clear. Okay. So now if I will go to data sample file, okay. So here can you see over here? What is my dependent variable? Consumption.
Yes, sir.
And my independent variable are x2 and x3.
X3.
Now what I will do is I will go and simply check the estimate the linear regression model. This is my y, this is my x2, this is my x3. Okay. So simply I will say okay. Now can you see over here?
Yes, sir.
Now I will ask you one by one. Is my regression is statistically significant? Sangeeta? Okay, question will pass. Chinmay, is the regression is statistically significant? Chinmay,
Yes, sir.
is the regression is statistically significant? From
Yes.
which test you are saying yes? From the F test.
F test.
F test. I told you how you will. First of all, what is the meaning of the question? The regression is statistically significant. Whether the x2 and x3, okay, the independent variable are able to explain the variation in the dependent variable, that is the consumption. Is it clear? Means in F test what we are doing? In F test, what is our null hypothesis? Our null hypothesis is beta 2 hat, or sorry, beta 2 and beta 3 is equal to 0. It means our income, the coefficient for income and coefficient for wealth is equal to 0. Is it clear?
Yes, sir.
Chinmay, in F test, what basically we assume? We assume the null hypothesis that all the slope coefficients are equal to 0. All the slope coefficients are equal to 0. What does this mean? What does exactly this mean? It means if your slope coefficients are equal to 0, now I will show you. Suppose let's say that the slope coefficient beta 2 is here 0.94, now it will be 0. x3, it is minus 0.04, it is also equal to 0. Then what is the purpose of the fitting this regression or estimating this regression? Yes or no?
Yes,
Are you
sir.
good? So what we do is we basically reject the null hypothesis to prove that our regression estimation is correct. Means if we will reject the H naught, how you will reject the H naught? First of all, you will calculate the F value. calculated f value. If the calculated f value is greater than the critical f value, then you will reject, the conclusion is you will reject the H naught. Okay. And Madhusita, how we will calculate f? What is the formula?
Sir,
I think each time you forget one formula, you have to pay me 10 rupees. Then only you will remember.
yes, sir. I basically in formula.
So there will be penalty. Now 10 rupees is little higher, so you pay 5 rupees. Huh? That is because we are economists, na? Then you will be very cautious. Sangeeta, is the penalty is fine?
Yes.
Yes, sir.
5 rupees or 1 rupee. We will keep 1 rupee for formula. Okay, Chinmay? We all agree?
Okay, sir.
Okay, very good. So F test formula is ESS upon degrees of freedom, Madhusmita,
Yes, sir.
and RSS upon degrees of
Yes,
freedom.
freedom.
It means, what is the degrees of freedom for ESS? I told you, it is K minus 1.
K
K
minus
minus 1. K is your number of
Observation.
Observe.
A. K
Sir,
is not
parameter, sir.
K is not number of observation. Like for example, in this regression, what is my K?
X2, X3.
They are not K. They are the variables, na. Coefficient are the parameter.
Parameter coefficients are
Can
parameter
Beta 1,
means
beta 2.
Beta 1 and beta 2 are the parameter, na.
so how many parameters are here?
2 parameters.
2 parameter.
Okay, 2 parameter. Very good. So here you can say because there are y is here and x2 is there, x3 is there, right? So it means our this is a how many variable regression? 3 variable, because in bivariate regression y and x is there. Now one more regression is there. Yes or no? Is it clear? Is it clear or not? So k is 3 over here. How much k? It is 3. You remember like this, it will be much easier. So if there is one dependent variable, means always there will be one dependent variable only, y, and there are 2 independent variable, then your k will be how much? 3. Okay?
The variables.
And if there will be, let's say that 4 variable regression, one more variable will be there, x4, then your k will be 4. 4 variable means 4, because we are including the parameter. Huh? K is actually, I told you na, that 3 variable case means your k is 3, and in the 4 variable case it is k is 4, and so on. Are you getting my point?
Sir, but in case of parameter, we add the intercept also.
In case of
Sir, as you say, in case of 3 regression variable regression model, we take the k value 3. Means we add the constant also, means intercept also.
K means only the variables.
K means variable.
Yes.
which is a k is variable. Yes, you have to remember like that. Okay,
Yes,
n minus k minus 1 we had discussed, na?
Yes, yes, sir.
Actually, we had discussed that, but now what we are discussing in case of F distribution, first of all, what is the degrees of freedom for the explanatory variable? Are you getting my point? So
Yes, sir.
explanatory variable is the degrees of freedom is k minus 1. It means if your degree, you can say if your number of k will be how much? That in three variable case k is 3, right? I told you. Now we can check also. I'll tell you how you will check. So 3 minus 1 will be 2. Yes or no?
Yes, sir.
Because for ESS I had written what? ESS degrees of freedom will be ESS divided by k minus 1. So how much it will be? If I told you 3, k is 3, then k minus 1 will be 2. Yes? And this will be RSS. What will be the degrees of freedom? Please remember, it will be n minus k. Okay? Is it clear?
Yes.
Sangeeta, is it clear? Or is there any doubt? Sangeeta?
But sir, in the RSS also we n minus k minus 1. We
No. First of all, I am focusing on the your on the F test. Okay? In the F test, I am focusing on the denominator and the numerator. Is it clear? So what you are saying? N minus k minus 1. You are saying.
1.
From
Yes.
where you have checked? Can you check the Gujarati book?
No, sir.
No, you tell me by that, sir, I got from the Gujarati book. In RSS it is saying n minus what you are saying, the degrees
N
of,
minus k minus 1.
you check first, you check is it n minus k minus 1 and you tell me which chapter and where it is, then I will
Sir,
ask.
in the lab we discuss ANOVA and there.
That is not, don't refer that. First you
Okay,
refer
sir.
to the where it is. Check the book now quickly.
Okay, sir.
Which chapter you will check,
Chapter.
or the after the class also you can check. Okay.
Okay, sir. Okay, sir.
Now whatever I am telling you, later on if you will have any doubt whether it will be n minus k minus 1 or n
N
minus
minus
k,
k.
now that you will actually remember, means, or you will cross verify later on, but right now let me complete it, the F test. Okay, so where I
Yes,
was
sir.
trying to do it. Now how my F is calculated? Simply first you remember, then we will come to the whether it will be, you remember that the ESS in case of multiple regression it will be k minus 1 and RSS will be n minus k. Clear?
Yes.
Now when you will reject the null hypothesis that all the slope coefficients are equal to 0, this calculated F, if this calculated F is greater than the critical F value, and what is, how I told you earlier also, F is, you are having degrees of 2 degrees of freedom, means you will have, in case of F distribution you will have a numerator and a denominator, because here can you see there is a numerator and there is a denominator. So you will write like this: if F is greater than F alpha, alpha means the level of significance, and in bracket you will write k minus 1 comma n minus k, means you are referring to the degrees of freedom of the numerator and the degrees of freedom in the denominator. Is it clear? Means I am writing whatever the F value I am getting, I will write F 0.05. Let's say that I am testing at 0. My alpha is 0.05. Then I will check with k minus 1 degrees of freedom and n minus k degrees of freedom. Now how I am going to do, I will show you here. You just see how it is written, 2, 7. right? Now I cross verify whether my formula is correct or not. So what is the total number of observation, Madhusmita? 10. Yes or no, Madhusmita?
Yes, sir. 10 observation.
So k, if my k is 3, so you just see how I have the software has given us f in bracket 2. It means the degrees of freedom it has given for the numerator 2, and for the denominator it has given 7.
7.
So as per the formula I told you, for the ESS it is k minus 1, because there are 3 variables including y. So that is the most easiest one. Don't get confused. Y minus means y including y, there are 3 variables in this regression model. That is why we are saying k is equal to 3. So 3 minus 1, 2. Isn't it?
Yes,
So 2 is as per our formula which I have written, there is no inconsistency. So the numerator is having degrees of freedom 2. Then 7, how it come? N minus k. K is 3.
10 minus 3.
10 minus 3 is 7.
7.
Is it clear?
Yes, sir.
Now we got F test calculated, F value is 92.40196, and because we are not software will not go to the table and give us, so already the simulated values are already there. So directly p value is giving us the alpha value. So how much it is, this number, how you will read this number? Is the p value, if I will ask you, is the p value is less than 0.05? Look at the regression result. Madhusida?
Sir, no, sir. Greater than.
How? Because it is a scientific number, na? I told you e minus 0.6 means after decimal point 0, after 0, e minus 0.6, like this if it is written. So after the decimal point 0.000 after 50, then the number will start. Means the number is how much? 929. Are you getting?
Yes, sir. Yes.
Then still you are saying the p value is not less than 0.05?
No, sir. Less than 0.5.
Very good. Even if it is less than 0.01. Okay?
Sir, first we cross check, means we
Let me
always
complete. Let me complete, then I will take
Okay,
your
sir.
question.
Okay, sir.
So now the p value what we got, it is less than 0.05 also, and it is less than 0.01 also. So then now you tell me, first you tell me my question. Now what we got, our rejection rule is, if our calculated f is greater than the critical f, then we will reject our null hypothesis which says the regression is not statistically significant or all the slope coefficients are equal to 0. Now based on my f value, can I reject my null hypothesis or I will accept my null hypothesis? Is my f is greater than f value? How I will know? From the p value directly. So p value is less than 0.05 means, or 0.01 means, my calculated f value is greater than my critical f value. Is it clear? Whenever p value, simple funda, if the p value is low, how much low? If it is less than 0.05 or it is less than 0.01, then you will assume that, means you will say that f test is statistically significant, means calculated f value will be greater than the tabulated or critical f value. Then what we will do? We will reject the null hypothesis, and when we reject the null hypothesis, in this case we say the test is statistically significant. Test is statistically significant. What practically it means, if the test is statistically significant when we are rejecting the H naught, means the regression which we have estimated, it is not a waste, or it is not like that, it is not explaining any variation. Our income and wealth is able to explain the variation in the consumption. Is it clear? It means the regression model is making sense. First of all, tell me the interpretation is clear or not. Sangeeta?
Yes, sir. Everything is clear. Just with the values, we are confused, sir.
Which value?
Whether P is greater than 0.01 or not. Only that point I'm getting confused, sir.
Means you are not able to read this, right?
No, this one I understood. But in every questions are the same thing. That when we are estimating the P value, whether it is greater than or less than. Actually, sir, I'm not able to calculate.
But this is here, there is a directly it is given. Na? Now let me see. Let me show you one simple thing. I will show you. So this is your P value. Okay. So how much Excel is giving you? 1, 2, 3, 4, 5, 9 to 9. I had written also the same thing. Yes or no? Are you getting?
Yes, sir.
So suppose what I will do is, I will increase my decimal point. Let's say that I will keep it to, this is a scientific number format, that is what I am telling you. If I will increase my decimal point to 6, or you can say 7, 8 total number, so I got this. Okay. So you are saying, suppose if I will take 0.05, okay. Now if I will ask Excel, is this my calculated P value is greater than this? So you think manually if you will do is, let's say that is logical. Is C4 is greater than D4. I think the formula is somewhere wrong or something has happened. But by looking at this value, what you can infer, Sangeeta? This is 0.0000929 and this is 0.05. So clearly we can say the P value is less than 0.05. Yes or no?
Yes, sir. This one I understood, sir.
Then
But
where is the problem?
no problem, sir.
No, under pressure you are saying no problem, or you have understood, you are not able to understand.
No,
Okay. You have understood, right?
but
So,
clear, sir.
which one?
This example I'm clear, sir.
Okay. Chinmay, is it clear?
Yes, sir.
Now you tell me whether the F test is statistically significant. Yes?
Yes, sir. Yes.
Yes, very good. Statistical significant means what? Means the regression is sensible, or regression is a correct one. Statistically correct. You use this word. The regression is statistically
Correct one.
correct or statistically significant. Okay? The regression is statistically significant. Is it clear, everyone? Madhusmita, now you tell me what is your question.
Sir, my question is, if we compare the P value 0.05, at the same time, why we compare with the 0.01?
Because it is like this, 0.01 always alpha has 3 values. 0.01, alpha 0.05, and 0.10. So what is the confidence level? It is 99% here, and this is 95% here, and this is 90% here, isn't it?
Yes.
Now it depends upon with what confidence you want to reject your null hypothesis. Suppose let's say that in the medicine field, or you can say health sector. So when a doctor is prescribing medicine, he has to make sure that whatever he is prescribing with a highest confidence level, isn't it?
Yes, sir.
But as a social science, we are actually, we have, it is not sacrosanct or it is a strict rule. You can be as strict as it is. Are you getting my point? So we choose in between, mid path. Okay, so it doesn't that there is a thumb rule that always we will set the alpha as 0.05, but it is in between that. Okay, and similarly it is 90% confidence level of confidence. Now you tell me, if a test is like p value, you got whatever the p value, if it is less than 0.01, then definitely it will be less than 0.05 also, na?
0.05. Yes, sir. Yes.
That is why I was telling you. And it is definitely, it will less than 0.10. But now let's say that if the p value is greater than 0.01 but less than 0.05, means let's say that you got a p value 0.04, right?
Yes.
So this is greater than 0.01 but less than.
0.05.
So that is the reason why I am saying when a test statistics is statistically significant at 0.01% level of significance, then definitely it is also statistically significant at 0.05 level of significance, because we had higher, if we are having 99% confidence on our regression model, then definitely 95% is in between, means within 99, na? Because 99 is a bigger number. Is it clear?
Yes, sir. Yes.
Or is there any problem?
No, sir. Clear, sir.
Okay. Chinmay?
Yes, sir. Clear.
Okay, very good. I think because you have missed few classes, maybe you will take, because just today you have written. So some time you will take to understand many things. So
Yes, sir.
now the question is, why we got to this f value and all. Now you just tell me, f thing is already, I asked you, regression is fine. Then we will go to our interpretation. Okay. Now you just tell me. Now I will ask next question. Sangita and Madhusmita. Is my, what next I will check? I will check R square also.
Yes, sir.
What R square is explaining? Chinmay, you know the R square, right? Very well. So you interpret. Interpret the R square. What is the R square value? 0.96.
0.96.
96350.
Right.
So simply your mind should run like this. If your R square value is 0.96350, let's say that. So you will multiply into 100. So you got 96.35. So it means your regression model is able to explain the 96.35% variation in the dependent variable y, or in this case the regression model means your income and wealth is able to explain 96.3%, means basically 35% variation in the consumption variable. Is it clear? The dependent variable. Is the interpretation clear? Sangeeta?
Yes, sir.
Okay. Now what is the next thing I will check? I told you earlier also. Madhushita,
Standard error, sir.
standard error. But standard error of the regression. Standard error
Yes, sir.
regression is also very low, 6.80. Okay? It's not very high. Are you getting my point?
Yes, sir.
Now what next I will, where I will go? How I will check? What I will check? Sangeeta? Next what I will check? I will check the t test, t value,
Yes,
the
sir.
p
T
value
test.
of the t test, because it is individual test, because that is why this t test shows whether the constant term, that is beta 1, whether beta 1 is equal to 0. This t test value for x2 is saying whether my beta 2 is equal to 0. This t test for x3 is saying whether my t test for beta 3 is equal to 0. And how I got this t ratio? Tell me the formula quickly. From where I will calculate, how it is getting calculated? Yes. Sangeeta?
Sir,
Beta 2
Beta
divided by standard error
standard
of
error
beta
of beta 2.
Okay? Beta 2 divided by standard error of beta 2. One experiment you can do. Suppose let's say that we'll take beta 2 is 0.941537. So I will paste it here just to show you. And what is the corresponding standard error? You can see that is so what I will do is this is my beta 2, this is my standard error of beta 2. So how much I got? 1.144. Now I will see whether my software has given this or not. Software has also given this. It means correct. Yes or no?
Yes, sir.
Or is there any problem? There is no problem, na? Right? Now, what is the p value? P value is 0.2902. Yes or no?
Yes, sir.
Now you tell me whether my null hypothesis, what is my null hypothesis over here in t-test? Because I am checking the individual statistical significance of the regression coefficient. So my null hypothesis is beta 2 is equal to 0. My alternate hypothesis is beta 2 is not equal to 0. Now, if my calculated t value will be greater than the tabulated or critical t value, which we are checking directly from the p value.
P value.
So, if this is greater than, then only we will reject the H naught. Okay? Now, so it means t value should be higher. T value should be much higher and p value should be much lower. How lower? It should be less than 0.05 at least. Okay? Now, you just see p value is 0.2902. So 2902. So what will be my conclusion, Chinmay? Is the test is statistically significant?
Yes.
How? 0.2902.
Zero.
Is it less than 0.05 or greater than 0.05?
Greater than.
Then how? I told you, no? Critical t value should be, means calculated t value should be greater than critical t value when you are having this condition. Means your p value should be less than 0.05, but you got p-value is 0.2902, which is much greater than even if 0. Alpha 0.10. So what will be your conclusion? Whether you will be able to reject H naught?
Yes.
No, because you will be able to reject H naught only when your p-value is less than 0.05. But in this case it is contradicting, na? You got p-value which is 0.2902. Are you getting my point? Chinmay, right? Madhushinda, is it clear?
Yes, sir.
So my p-value is much higher than 0.05. So that is the reason I will actually fail to reject the null hypothesis. What is my null hypothesis? That beta 2 is equal to 0. Now you will say, sir, the coefficient is 0.94. How I will say that? Because from the t-test, I am concluding that it is not statistically different from 0. Okay, it means I have, even though you got 0.94, but I will consider that it has no impact on the regression. How? Because from the t-test. Is it clear? Chinmay now?
Sir.
Tell me. Not clear. So you ask me day after tomorrow, or I'll discuss with you. Sangeeta, is it clear? Chinmay, where is the problem? I have told you simple rule of thumb. If the p-value which you got 0.2902, if it is less than 0.05, then only the test is statistically significant. Means you will reject the H naught. Okay, that beta 2 is equal to 0. Now you got 0.2902, which is actually higher than 0.05. Now simply you will fail to reject the null hypothesis, which says beta 2 is equal to 0. Are you getting my
Yes, sir.
point?
Yes, sir. Yes, sir. Yes, sir.
Now where you had a confusion? What you are thinking? Chinmay? Okay, fine. Not a problem. Now you have understood the regression. So
Yes.
X3, now I'll ask whether X3 is statistically significant, Chinmay?
X3.
P-value, look at the p-value again. 0.6151.
0.61 is greater than
0.05.
0.5.
Yes.
So
So it is not statistically
not
significant.
statistically significant.
So it means beta 3, the null hypothesis will be beta 3 is also equal to 0. Means you will feel statistically not significant, means you fail to reject the null hypothesis.
Null hypothesis.
So what is your null hypothesis? Beta 3 is equal to 0. Okay? Are you getting?
Yes, sir.
Now the constant term. Now the question is, Madhusmita. No, let Chinmay to answer. For the constant is it statistically significant? The constant means the beta 1, the intercept.
Beta 1 intercept.
Means beta 1 is here, na? Constant. Constant is beta 1, na? This term, that is beta 1. Is it statistically significant? Chinmay?
Yes.
It is yes. Why?
Because
The p-value is
p-value is
less than 0.0.
0.000.
Very good. But also one more thing you are not able to observe, means I have not told also. this 3 star in the software it is much easier, but in exam or somewhere it will not be directly given. But usually in the regression output we read 3 star means it is statistically significant at 0.01 level of significance. There will be 2 star also, there will be 1 star also, 2 star for 0.05. So directly you will not face any problem. Only you look at the star and you will be able to tell. You just see for 0.2902 there is no star. For 0.06151 there is no star. It means the test is not statistically significant. Okay. Now my problem is there any multicollinearity in this data? Because that is the reason why we had estimated this regression, na? Isn't it? Madhusudha?
Yes, sir.
Now, is there any multicollinearity problem?
No, sir.
First of all, I am telling you, there is no multicollinearity problem. You are saying, right?
Yes, sir.
Very good. But there is no multicollinearity problem. Everything is good, and you are also getting that x2 and x3 is not statistically significant. Then you are not getting any problem over here. Regression F test is also very high, F value. So everything is fine over here, right?
Yes, sir.
But these, how you are saying, only the intercept is statistically significant, other two are statistically not significant. What does that mean? I am again and again I am telling you, na? I am telling you that beta 2 is equal to 0 and beta 3 is equal to 0. You are saying beta 2 is equal to 0 and beta 3 is equal to 0. Then why the hell you are running this regression? Are you getting my problem?
Yes, sir.
Means there is no point, na?
Yes.
Because these two are not statistically significant. It means your numbers you are not able to defend. That why you have run this regression. So everything is not correct. There is some problem over this in this regression. Are you getting my point? Even though R square is very high, F is very high, then these results are misleading us. Are you getting? These results are misleading us. Ideally, we should get 3 star or 2 star, or at least it should be statistically significant x2, but we didn't get it. So that is why this is one of the implication of the multicollinearity problem. There is a problem. Are you getting? Why?
Yes.
The standard error is very low. You can see over here. Means standard error. Can you see over here? Standard error is low, but still the T ratio is not actually statistically significant. Okay? Are you getting my point? It means a high R square. Just now I told you, in case of multicollinearity, what is the problem? First, you should know a high R square, but I had written, na? But few significant T ratio. Is it clear?
Yes.
Right? Is it clear?
Sir, actually, high R square, it is clear, but the significant ratio, T.
Significant T ratio, na? Significant T ratio means few significant T ratio means T ratio is not statistically significant. Among these three, we have estimated beta 1, beta 2, beta 3. Beta 2 and beta 3 is statistically not significant. Isn't it?
Yes, sir.
Is there any problem? Understood?
Yes, sir.
So you will never forget that in case of multicollinearity, what is happening? You are getting higher square, but you are not getting statistically significant T ratio. Means The variables, there is some problem with the variable. They are highly collinear. Okay. Then what is happening over here? When you are testing the null hypothesis, beta 2 is equal to 0, we are using T ratio. The formula is also I told you, beta 2 upon standard error of beta 2 hat, right?
Yes.
Now, in case of high collinearity, the estimated standard errors increase dramatically. Therefore, we are getting p values very small. Okay. So, in such cases, you can accept the null hypothesis that the true population value of the beta 2 is equal to 0. It means it is not making any sense in your regression. Is it clear?
Yes.
Chinmay, is it clear?
Yes, sir.
Okay. And so detection, this is one detection. In case of multicollinearity problem, so you will find that very high R-square value of the regression and less statistical significance for individual coefficient. Another, first is this, okay? This is how you will detect. Second, you will say high pairwise correlation. High pairwise correlation among the independent variable. Are you getting?
Yes.
Correlation among the independent
Very.
IV. I am writing. Now how I will verify this? Just see. I can do go to file, data. So what I will do is I will select these two variables. You just see how easy it is to learn econometrics. So correlation. How much it is coming? 0.9989. It means they are close to 1. Are you getting the problem? Now we have identified the problem. What is the problem? Chinmay, what is the problem in this regression model?
There
Chinmay,
is a high
there is a multicollinearity problem. What is the problem?
multicollinearity problem.
How you got to know this? That there is a multicollinearity problem?
Because there is R square
R-square is very high. And
very high.
then?
And significance ratios.
No. There are T ratio is not statistically significant. Right? Few significant T ratio. Okay? For the slope coefficients. For the slope coefficient or the parameters. For the slope coefficient. Are you getting? Then high pairwise correlation among the independent variable. Is this two condition? Because of this two reason we are having multicollinearity. Is it, Madhusudha, is it clear?
Yes, sir.
Or is there any problem? Chinmay, is it clear?
Yes, sir.
Somehow it is clear. Now next I will ask you, because already I think we had discussed yesterday also. So OLS estimator, what will be impact on the OLS estimator? If you are, already I told you how to detect, everything is fine. Now is the OLS estimator is blue? OLS estimator are having large variance. So now you can say they are not efficient. Correct? That is the reason. Now coming to VIF, how you will calculate VIF? So VIF is basically called variance inflation factor. Okay, because variance is causing the problem, na? That is the reason why we are actually Because we told just now, I told you that if there is a multicollinearity problem, variance of the estimator standard error basically it will increase. So how we will come to know? We can calculate directly 1 upon 1 minus r square 2 3. Means basically, so r square 2 3 is basically, what is r square 2 3?
Beta 2, beta.
Coefficient of correlation between x2 and x3. Suppose in our case, how much we got? R square 2 3 means 2 variable and 3 variable. We got how much? We got 0.99896239. Are you getting my point? Is it clear? So what is our R square? 2 3 is 0.99896. So what is our formula? How we will calculate VIF? We will calculate VIF 1 divided by, in bracket, 1 minus r square 2 3. Okay? How much we got? Very high value. Are you getting? Let's say that is it a number. Let me say it a number first. So yeah, this is fine, not a problem. Is it so high? I'm not sure. 1 minus z5, yeah. So it is fine. Let me see the test is there. Here it is saying test or not. Here. Yeah, VIF is not visible over here. Not a problem. Is it clear? VIF is
Yes,
very
sir.
high. Are you getting?
Yes, sir.
So what happened over here? Because the formula is, VIF formula is 1 minus r square 2 3. R square is correlation coefficient. Are you getting my point?
Yes, sir.
Correlation coefficient between x2 and x3. So when this is in bracket, so if the r square 2 3 will close to 1, means I told you maximum perfect correlation will happen when the value will be 1, right? Perfect
Yes,
linear
yes, sir.
relationship. So 1 minus 1 is 0. So 1 upon 0 is close to infinity.
Infinity.
So that is why we are getting a very bigger number. And I was not able to, even if I got surprised also. Are you getting my point?
Yes, sir.
So VIF is approaching infinity. Okay. So what we can conclude over here, when the extent of collinearity increases, okay, the variance of an estimator increases, and in the limit it can become infinity. Okay, then there is a problem. Then there is a very severe high collinearity problem. Now actually from the VIF we usually like suppose if you will say how much bigger your VIF should be. So better it is you can say rule of thumb is not there, but you can easily say that if the correlation coefficient is equal to less than 1, so it is better. If it is close to 0, it is better. Okay. So if the VIF is, because from the formula itself, like if you will ask me, sir, how much VIF we should have, because you are saying if the VIF is towards infinity, then the model is suffering from multicollinearity. Let's say that if the r square 2 3 is very low, 0.23, we'll take 0.23. 0.23 is very low. Let's say that. So what we will do is, we will do 1 upon, we are assuming it, okay, 1 upon 0.23, means this is a correlation coefficient between x2 and x3. If you are assuming, how much we are having? 1.29. Can you see the difference?
Yes, sir.
There is a significant difference. Are you getting my point?
Yes.
Means the moment the correlation between x2 and x3 has reduced, the VIF also reduced because of the formula. Are you getting?
Yes, sir.
Or is there any doubt? Sangeeta? No. Now, what is the solution of the multicollinearity? You have to transform the variable. Okay, different type of transformation you can do. I think yesterday already we had discussed. So, or you can drop some variables which is causing the multicollinearity problem. That is the also solution. So I think I will stop over here because we have discussed at length multicollinearity problem. But don't forget, okay?
Yes, sir.